Okay, we're at the last section, 22.7, total internal reflection. Let's look at the slide here. That as the angle of incidence theta 1 increases, the angle of refraction theta 2 increases until theta 2 is equal to 90 degrees. That's ray 4. That's this one here. So the dashed line indicates that no energy actually propagates in this direction. For even larger angles of incidence, the total internal reflection occurs. That's ray 5. The angle of incidence producing an angle of refraction equal to 90 degrees is the critical angle theta c. At this angle of incidence, all the energy of the incident light is reflected. So this is now this has to be, I believe N1 has to be greater than uh, N2. So this would be like glass or and this would be air. So the figure says rays from a medium with index of refraction N1 travel to a medium with index of refraction N2, where N1 is greater than N2. So, again, this would be like water, glass. In the next example, it's diamond. So let's look at the diamond. N1 sine theta critical equals N2 sine of 90. Well, what is the sine of 90? That's equal to 1. So it's just equal to N2. So the sine of theta critical is equal to N2 over N1 for N1 greater than N2. The diamond has an index of refraction of, here it says 2.42. So the theta critical is 24 degrees. For crown glass, N is equal to 1.52 and theta critical is equal to 41 degrees. So the property with theta critical being 24 degrees for diamond combined with the proper faceting causes the diamond to sparkle brilliantly. Okay, and total internal reflection on a prism, you can see how it is 45 degrees. It also can do 180 degrees. It can also be used for like a periscope. The two prisms used as a periscope, and then the one that we use all the time in technology is fiber optics. This uses total internal reflection, so all the energy goes down the fiber optic cable, and that's it basically for the rest is a topic summary. That's it for chapter 22.